government and also people, taxpayers, and so on, whether they would like to contribute to science in this way or not. And practically, after BPC2, this perfect timing. Technology is easy because, relatively easy, because we have Beijing Electron Positron Collider running for the last 30 years. And although the machine is small, but the E plus minus collider is the same everywhere. So this is a small machine, actually have all the components there. So it's not completely new. And we have a large and a young population, and the turn of construction will be cheap in the near future, not certain, not in the far future. So if we can do it now, we should just do it now. And this money, I mean, is there, right? So if we don't take it, material scientists will take it, or life scientists will take it. So we should try our best to get our sharing. And this sharing is not exaggerated. It's reasonable. It's normal.
I just wonder, how do you scale GDP to 2036?
Oh, you assume a 6% increase. You think it's too high? 6% is it's feasible, right? And this number is not by far, and this number I already put safety factor here. People always asking about the relationship between IRC, between ASC, and also the CERN's initiative of FCC. So our opinions is the following. CEPC is our main goal now, and the SppC is in distant future. But FCC, they would like to build as soon as possible, even now, starting from 2020 or something. We're talking about this. Where they can get money, nobody knows, and very few people believe that they can get money at that time. But anyway, I know that CERN is working on it, and they try to get there. So we have different strategy, different approach. Who is the best? I don't know, but at least I mean, I don't know what your opinion is. I know my opinions. My opinion is very clear, and CEPC plus SppC is the better solution. Or electron machine plus proton machine afterward is the best solution, not the other way around. We have to design the CEPC to maintain the possibility for the SppC, and so in the future you don't have major changes of internal infrastructure and so on. You can easily just install your new machine. CEPC and IAC are complementary, and IAC can happen at any time, any moment. A lot of people saying that in the whole world we should get one machine, not too expensive. But up to now, there's no success. The agreement among particle physicists doesn't mean that you're going to get agreement from the politicians and the government. So before you claim we can make only one machine, before you claim the whole world will jointly make one machine, it's not going to work, and at least not working yet. There are a lot of difficulties. If there's no competition, nothing will happen. You all know this, right? So once I told my colleagues in ICFA. ICFA stands for International Committee for Future Accelerators. So I was joking that I came from a communist country. I'm teaching you guys what is the good of the competition. So for the IRC, I believe we can help them by removing the push-pull option. So I think the IRC having a push-pull option is not a good idea, at least, and very few people believe that you could do it, and from physics point of view, you're not going to gain anything. You're actually losing time for this push-pull option. I'm not sure you all understand what does mean the push-pull option. The linear collider can have only one collision point, but a lot of people want to do experiments, so they decided to build two detectors. So every half years, you move one detector in the equalization point. After half a year, say go, and then another one comes in. After another 5 years, you say go, and come the new machine. This machine, this detector is huge, right? Several thousand tons, all the cables and so on. Once you cut it, switch it off, and you do moving it back and forth, you lose at least 20, 30, or 50% of your running time of the machine, possible timing. So I think this is a terrible solution, and having the CPC and IAC together, we can have multiple machines, multiple detectors. I think it's the best for the future of our field.
Only slightly.
Yeah, I mean, I don't know. I mean, it's not going to. It's not. Well, you can do it, but the detector is large enough. I mean, small one, you all did this, right? And test beam, you always have your equipment moving in and out. It's small enough, easy. And this one is huge. So, let me give you a report on the current status. So we initiated a global effort for the conceptual design. The pre-CDR has been finished. It's on web. There's no showstoppers. Technical challenges identified, so we know what we should do for the R&D. And also we have the preliminary estimate of the cost. We already got money from IAMS with very limited resources. Every 3 years, for the next 3 years, we will get 12 million RMB. So this is like $2 million, nothing. And most is probably interested to give us roughly 100 million RMB for the next 5 years. We hope it can happen next year. The National Commission for Development and Reform, we would like to ask 1 billion RMB to them, but it has not yet been started. So the process is very difficult and complicated. We're still working with them. Our future goal is to have a CDR by end of the next year. Because up to now, this pre-CDR has still a lot of flaws and a lot of things we do not understand. And the design is not detailed enough that the machine can be understood fully and can work. So basically, in other words, the existing machine, the existing design in the pre-CDR is not a working machine. So there are some conflicts and troubles, issues there. It's already identified. We hope by end of the year we can, next year we can solve all the problems. We also have to select the site, and we have to have an international organization and so on. Our dream timeline is the following. For the CPC, we finished this pre-study, pre-CDR, and this document will be used for the funding request for the R&D. And then starting from next year, we will work seriously on the R&D and the detector and also the machine. We are going to study also the engineering design for the servo, for the terminal, for utility, and so on. And the final construction hopefully can be started in the year between 2020 to 2025. Anywhere in this time, and before 2030, we should stop taking data. And if we take 10 years of data, 2030 becomes 2040. So it's a little bit aggressive of a few years, but I mean, 2035. I don't know where I am. I don't care if there's a 5 years difference or not. So SppC, we're going to have a pre-study by end of 2020. R&D will start in 2020. This is the time when we finish this R&D and we start construction there, and now we can have our hands free to work on the R&D of the SppC. Of course, we have to do the engineering design. Construction will take another 10 years or 7 years, and the data taking will will start something like 2045 or 2046 or something. So if we take, say, 15, 20 years of running, we end up 2060, 2070. Most of people in this first line, they all disappeared. It's a planning for people behind it. So this is the design report. First volume is physics and detector, and the second volume is accelerator, and then we have third volume is civil construction. So in total, well, this is 700 pages, another one is, so about 1,000 pages of a document, preliminary design document. You can download from here and have a look. So these are a few plots. We invited the world famous scientists to review our pre-CDR, and with their endorsement, we put the document on the web. So you can see that we have 4 different groups to review this document. So very short introduction about how the detector accelerator looks like. So we have a LINAC going to a booster, accelerate the energy in the booster, and then inject the 120 GeV particles into a storage ring, and then somewhere they can collide. So this actually is 3 machines in 1 tunnel, and our main choice of CEPC at this moment, strictly for the cost reasons, that we're going to have 1 real machine, and the collision will be head-on. CERN's FCC is 2 real machines, so you have to increase the cost by at least another factor of 30%, something like that. So for this 30% of cost, we decided to go to the 1 real machine. Compatibility is a very complicated issue. So you see this is a detector, another 2, I think this wrong, this should have another 2 detector and coming out. So 2 will be for the electric machine, 2 will be for the proton machine. You see all these little terminals getting around, it's very complicated. We try to make sure that we are not going to regret after we finish the electron machine. Once we want to install the proton machine, we say, oh, sorry, we can't do it. I mean, it's underground, right? It's very hard to re-dig some space you need. So you have to make sure that what you dig is suitable for the future. So this is machine design. The key is the luminosity, 2 × 10⁻⁴, and this is a factor of 2 to 3 higher than IRC, and we have also 2 interacting points. This is another factor of 2 on the number of Higgs. So this is at least a factor of 5 more Higgs than IRC. These are some choice of parameters, and these are calculations. So I'm not going to talk about this into details. This is a list of challenges we have to solve in the next 5 years. First is the machine physics design. So we have to understand the dynamic capture, momentum acceptance, electron cloud, and pressure schemes and so on. These are all the accelerated physics problems, not yet solved. We have to figure out all of these issues by end of next year. We need to build the superconducting cavities. We have to have a very high Q value. We have to solve the home damping issues, mass production, power consumption, and so on. So it's a long list of issues we have to solve. The third big issue is that the total power consumption is 500 megawatts. So this is, if you take 1 reactor, it's 1 gigawatt. So this is half of a reactor. This is huge power consumption. So we would like to reuse a lot of this energy actually is vented out. So if we can use this 200 megawatt, reuse it, then we can save a lot of the cost of electricity. There are many ideas. Some of them are very real. So if you have suggestions, please let us know. It's a big issue for us. Of course, you can think that this roughly 50 degrees of water, so it's not very hot. So this 50 degree water we can, for example, send to people's house. So this is something that heat your house. I think it's a good way to reduce it. And another possibility is to heat the liquefied natural gas. Okay? That you don't need a lot of very high temperature, because all the liquid came from all the ships, big containers, are all in liquid form. So you have to gasify it so that they can transfer through the pipes. So we can use this, but you have to near a harbor. So Qinhuangdao is a good place because it's a major harbor for imports of natural gas. Of course, you can do it for the agricultural greenhouse, but in summer, so this one also cannot be used in summer. So it's so we need to find even better solutions. So ICFA has now set up a panel to discuss the so-called green machines. So everybody now realizes this problem. So we have to talk about the green machines and try to reuse this energy. Extremely important. Another direction we should work on is to increase the efficiency of the RF power, radio frequency power. These are the key to the experiment, and we hope, right now we assume 55%. So we would like to increase this to 70, even 80%. There are people working on it. And also another idea is to build half double ring machine. The so-called half or partial double ring machine is following. In most part of the terminal is a single ring machine. When you go to a place which is very close to the collision, then you make two rings. So in this case, you have an electron, positron. They go through different pipes, and the luminosity can be increased. So once you increase the luminosity, you can also argue that I can fix the power assumption and reduce the luminosity. So by doing this, you get the same luminosity, but you consume probably not 500 megawatt, but maybe 300 megawatt or 400 megawatt. So this is a way to solve the issue of energy consumption, and also from a machine point of view, with double ring, it is actually much easier to get higher luminosity. The pressure scheme in the one ring for the electron positive collider is very, very difficult. So we have people working on it, and papers, and so on. These are actually the key questions we are working on, and we hope by end of the next year we can come up with a simulation that demonstrates this can work. Our preliminary calculation shows that this is feasible. So the biggest component or most difficult component of this machine is the superconducting RF cavity. So we choose for the collider and the booster different frequency. One is 650, another one is 1.3. And we have 700 of them. And we have many of details, specs, and so on. We try to work to start the R&D for this cavity. And this is actually the only showstoppers. It's not showstopper. It's the only biggest issue that nobody knows in the world at this moment how to solve the problem. Many of the others, somewhere in the world, at some corner, there are people say, I can do it. We can talk to them. But this one, nobody knows. So we have to work out and come up with a solution. This is a proton phase. SppC stands for Super Proton-Proton Collider. A lot of people argue that this is the wrong name, and it makes people think about SSC. It's not very lucky. It's not a very lucky letter. So if you choose 50 kilometers, a low magnet, you get 50 TeV. If you choose 70 kilometers, 20 Tesla is 90 TeV. So If you choose 80 kilometers, 100 kilometers, you can easily get 100 TeV, no problem. This is a generic design. You see this is electron interaction point, and these two are the proton interaction point. So these are some parameters. Not going to talk about details. Of course, this has a big challenge, very high magnet, 20 Tesla, and we have also other issues like a beam screen and the collimation system, so on. So details are not going to cover. And this is our design, which has this very strange shape and also the distribution of the magnetic field. But one thing I would like to emphasize that this is our design, which is different from all the other dipole magnet in the world. It's a special design. The other one, other experiment like HT so on, they have this thing turn 90 degrees. Once you turn 90 degrees, it's very bad because this part, the synchronization, will affect your magnet. If you do this way, synchronization go this way. If you turn around, synchronization go this way through your code. This is very bad. So turn 90 degrees is a break level kind of change. My personal feeling is that the future magnet has to rely on the high TC. The current design to get 20 Tesla is to build two magnets. One is 15 Tesla magnet of low temperature kind of coil, and then you put the 5 Tesla magnet inside of this traditional low temperature kind of magnet. And this combination makes the construction very complicated and very expensive. So we still have 20, 30 years. So my hope is that we can use HTC. This curve is the development of cables in the last 10 years, and also extrapolations to 2020. The price came down over the years with some kind of ratio of 2.5 times per 10 years. And the current limit, you see they're going up. It's also increased by roughly 3 times per 10 years. This blue one is from Chinese from this one, green one. Green one is Shanghai superconducting technology, whatever company. So you can see that it started late, and they're going down much faster than others. And this one is the current limit going high. I believe this is Shanghai product. The others slightly kind of flat. But generally speaking, of course, nobody can guarantee what's going to happen in the next 20 years. But I think we have to remain optimistic. What happened in the past 10 years is that we improved everything by a factor of almost 10, right? Or maybe 5. So if we assume you get the same improvement kind of speed, then per unit price is ampere per meter can improve by 50 times over 20 years. And this is good enough for this factor of 50. So, of course, now HTC kind of cables is still too expensive, difficult, so on. But I believe 20 years from now, it will be very different. This is another comparison of the price. So these are the price purchased by people in Berkeley several years ago. We don't know exactly how many years. Maybe 5, maybe 7, maybe 10. This is the price. And this is the quote from Shanghai. It's 2,400. You compare to this one, is 20,000. And the YBCO is new one, it's $3,000. You can see that the cost is already come down quite a bit. So I think we have to remain optimistic, not to concern too much about the future. So this is CEPC Detector, this drawing. It came from IAC IAD Design. It's a requirement, and there's something very specific, special. One is the air star. It has to be shorter than IRC, and we cannot use a pulsing kind of scheme. So the cooling is a big issue for the circular machine, and for linear machine they are okay. Good news for us is that the radiation background in the circular machine is smaller. So we have a long list of detector R&D have to worry about: the vertex tracking, colorimeter, magnet, and so on. Technologies involve the silicon pixel, silicon strips, not silicon pad. Oh yes, silicon pads, and the scintillator pads, RPC. So RPC will be for the mirror chamber. Hadron colorimeter can use scintillator pads, RPC, and EM colorimeter can use silicon pads or scintillator pads. Tracking device can use both, and the vertex will use the silicon pixel. We did some simulations to study the physics potentials of this machine. You can see these are the different channels, diameter, dielectron, and these are different channels. Green one with the full simulation is this, how do you call this color? I don't know, bluish, a little bit.
Faster simulation.
Yeah, this bluish kind of thing is for the fast simulation. And then there are things which we never did a true simulation, just in traffic. So finally, let's talk about the site. Okay, Beijing. Style. Anyway. Almost finished. This is not. So this is Qinhuangdao. So you all know where Qinhuangdao is. The starting point of the Great Wall. That's why people talking about this great machine and the Great Wall. These two things can be connected. It's 1 hour far by train and 3 hours by car. Almost exactly 300 kilometers. It's a very nice place. You all know that Beijing is terrible on air pollution. This is the best place. And in China, or in north of China, they almost had no issues of pollution or smog. So you can work there and also enjoy your life.
How about earthquake? It's close to Tansan, right?
Yes. Close to Tansan, but there's a fall to cut these two regions separately. So during the Tansan earthquake, Qinhuangdao did not get any effect. They are very safe, no problem at all. And no one died. So we have to worry about the civil construction. I think this is actually the key, and everybody knows that when you have a civil construction, you'll get enormous troubles with overrun of your budget and delayed and so on. And a terrible, low tech but a terrible issue. But anyway, we understood the issue and the problems, come up with a design, and also this is a lake, so we have to avoid. This is the underground tunnel. There's a little mountain here, and we also have to avoid. And these are the imagination of the tunnels underground. And you can see these are very special. It's a red line. These are synchrotron light on this machine. So the energy of this can go all the way up to 20 and very high brightness and a very high energy. I imagine that the applications of this beam line will be extremely interesting